In today's episode, a well-known issue made its appearance.
It's packet loss.
Then, an unexpected personality appears.
In 45 minutes, Obama is going to learn your name.
And finally, we're pondering the use of force.
They were going to start destructively busting stuff down.
Settle in for this episode of Cisco Tech Stories podcast.
Welcome to Cisco Tech Stories, a podcast with real-life stories from real-life engineers. Your hosts are Nicholas and Tristan.
Hello and Happy New Year. Welcome to the first episode of 2026 of the Cisco Tech Stories podcast. We hope you liked the style of the previous episode where we focused a bit more on technologies like quantum computing and AI, a bit different from the roots of our tech stories. So please let us know in the comments of your podcast app like Spotify. We are always open for feedback and ideas.
And talking about feedback, actually our next guest was suggested by one of you in the comments of a previous episode. So we got the guest, Kristopher Gabrielsen, Principal Engineer in NAND Switching from our tech center in RTP, North Carolina. Chris has a lot of experience and a lot of troubleshooting stories to share, and we hope you like this episode.
So without further ado, let's welcome Chris. Hello, Chris.
Hi, Chris. Welcome to the show.
Yeah, thanks for having me. Super excited to be here.
Can you introduce yourself and your career?
Yeah, absolutely. So my name is Kristopher Gabrielsen. I am currently a principal engineer within the enterprise networking segment of Cisco Tech, also known as CX. And I've been with the company for, I would say, a little over 15 years now. I started back in December of 2009. I started as an intern. It was one of my requirements for my computer networking degree. And I ended up starting in the lab doing cabling, rack and stack of gear, power and stuff on. Pretty simple stuff. And I didn't screw it up that bad. So Cisco asked me, hey, why don't you come back, do another rotation? And so I started on a TAC team as, again, another intern, this time a second-year intern. And that's where I fell in love with the technology. And I made a career out of it. I started with our switching team. I very quickly became one of the team leads for that particular team before then becoming a technical leader. I stayed a technical leader for about 8 years where I think your audience knows it, but there's a lot of the largest escalations in Cisco usually go to the technical leaders and get solved. So lots of war stories there. And then recently, in the past couple of years, I was able to get the principal engineer position. So now pretty much anything related to switches or enterprise networking, a lot of business strategy, that's kind of my purview now. A little bit less technical, but I do like to dip my toe in it from time to time.
I think as a principal engineer and technical leader before, you had a few high profile escalations, right? Like we have senior people who can handle like technical escalations,
Yes.
but whenever it's high profile, it goes to you, right? Do you have a few stories around that?
Oh, absolutely. And to say I have a few is an understatement. I think one of the things, and I'll do a quick aside here, one of the reasons I loved working on the switching team was if we think about most computer networks, and hopefully this rings true for people out there, one, maybe 2 times a year, you might have a big issue where something goes down or it's sort of a big deal. The benefit of working in TAC, we would see 3 of those a day per engineer. Every day you might have 15 to 20 catastrophic network down type scenarios. And so if you think about working on one of these teams for 5 or 10 years, even some of the more routine things become fairly common, or uncommon issues, you start to develop patterns and you get some of these high profile items. Some of the more interesting headlines that I think you guys might find interesting. I had one time a company related to nuclear fuel processing, and I don't want to get too specific there, but they open up a severity 1 issue and they say, yeah, the network's down and we need to get this up. This is kind of a big deal. And most customers that, yeah, I get it, where everyone thinks we're a big deal. And they say, no, you don't understand. If we don't get this network up in the next 45 minutes, we are required by law to declare a national security event, and the president gets notified. And I'm like, oh, you, like company president, or, I deal with that a lot. No. The president, as in 45 minutes, Obama is going to learn your name. And Granted, I always wanted to meet the guy, but not necessarily in that particular circumstance. But that's like one example of some of the issues we had. I had another one where this was hospitals, by the way, extremely common, and I think this is an interesting element of computer networking, especially having been in the industry for 15 years. You see just how interconnected everything becomes, and how much of in hospital environments, everything from like patient monitoring to door and medication controls and security system, everything is connected. And so this hospital was completely down, network was completely melted, and they said, "Look, we have the fire department. We have about 2 trucks worth of people that are waiting outside of this door with axes and saws, and we have 28 minutes to bring this network up, or they are going to bust this door down." I'm like, why?
I always think that Wi-Fi is important in healthcare nowadays, but if you got no switches, then you got nothing happening.
Yeah,
Not even
if
the
you don't-
doors, apparently. So
Exactly, right? It's the Wi-Fi is running all the remote patient monitoring, so all these nurses can't see all the patient vitals because now none of it's done manually. It's all automatic over the wire. And in this case, their heavy pain meds and some of the more short-lived medications, the really hard stuff, I guess you can call it, was all behind a locked door that was filled with security controls. When the network is down, the door does not unlock. The badge readers do not work. The medication dispensary fails completely. And you can't tell a hospital patient who is in tremendous pain, "Oh, I'm sorry, we can't give you this crucial piece of medication because the network is down." Like those two things don't make any sense. So, they called the fire department as a backup, and they were going to start destructively busting stuff down in order to make things work, all because of, in that case, that one was an L2 loop, which, by the way, L2 loops, very common back in the day. They're a little less so now, but that was probably one of our number one issues.
but what's your reaction then? Because I was going to ask, both for the nuclear one and the healthcare, if the situation is simple, like, one switch died, you can do a failover, like you can reasonably be certain, you can recover it. But an L2 loop, like finding the source, we've heard, is really not easy. So how do you feel about, how confident are you that you have either like 27 minutes or 45 minutes in each of the cases?
Well, let's put it this way. Obama never learned my name. And that fire department, I deprived them of what I assume was a very fun time busting out some doors. Calling back to what I said earlier, when I was on this team, I would routinely take anywhere from 1 to 3 severity 1 network outages per day. And as a result, I got really good at finding some of those issues. And in the case of L2 loops, at first, I agree with you, they were difficult to figure out, but eventually they became almost trivial. And I have a 3-step process. If anyone out there ever runs into a loop, they're actually quite simple to solve. The number one command is you look at your interface input rates across the switch. Just a simple show interface pipe include is up pipe input rate. That gives you the name and how many packets are coming in. And just look at which one is the highest, and it's usually going to be over 1 million packets per second, which in an enterprise network is pretty excessive. In a data center where we got big data flows, if we're talking like Netflix streaming or something, they're going to be moving a lot of packets. But for your average enterprise level network, if you're seeing 1 million, it's almost always abnormal. And so I look at the show interface input rate, figure out where it's coming from, because the symptom of a loop is always there's going to be 1, maybe 2 interfaces with a very high input rate. Everything else has a high output rate. Ignore the output rate. For those interfaces that are high, check show CDP neighbor, log into the next device, rinse and repeat. Keep doing that till you're going to end up in one of 2 scenarios. Either you have no CDP neighbor, at which point you just shut that port down because that's usually the source. It's connected to something it shouldn't. Or you end back up on the same device that you started. And at that point, now if I came back on the same device, it's like, all right, well, the only protocol that should be preventing this is usually spanning tree. Not a lot of people running rep or some of the alternatives. So take a look at spanning tree, and sure enough, you could easily figure out, oh, this device is root, which means this port should be blocking, and you shut down the port that should have been blocking, and 9 times out of 10, that clears the issue.
Sounds like a stupid question, but spanning tree is there to prevent the loop. So what is the cause when there is a loop? I know one possibility, because in wireless we just bridge VLANs over the air, and then we do crazy shenanigans, and then we create the loop over the air. So we do cause that a lot in our lab. But in your eyes, what are the most common cause of loop, and why spanning tree didn't catch it?
Yeah, so I think there's maybe the top 3 reasons that I found. One is third-party devices. People love just bringing stuff in from home or connecting something that they shouldn't, and we have no idea what the configuration is, and just plugging it into the switch. And in days where we have features like port fast does not mean the port goes faster. It just means it creates your loop that much faster. And as a result of plugging it in, we usually get a pretty immediate symptom. Port fast by itself, though, not necessarily a bad thing. It delays the whole spanning tree process. Normally it takes 52 seconds to go forwarding. But yeah, third-party devices are probably number 1. Number 2 is engineers out there that spanning tree being a pretty fundamental protocol, we tend to gloss over it a bit. And we think, oh, the more features I have, the safer I am. And I've seen quite a few networks over the years where customers go into the interface level config and they configure spanning tree, port fast, BPDU guard, root guard, loop guard, and BPDU filter all on the same port, hoping that more features is more security. For anyone who is not in the know, all of those features I just mentioned directly conflict with one another. BPDU guard says this should never receive a BPDU, whereas root guard says this should get BPDUs, but it shouldn't be the path to the root bridge. And loop guard says, well, actually, you should always get BPDUs, and if they ever go missing, that's a problem. And then BPDU filter says, I don't care about BPDUs. Don't send them, don't process them, don't receive them, don't do anything. And BPDU filter is the big one that combined with those other features due to usually ignorance creates a loop. And then I'd say the third most popular reason is likely just defects or little issues that come up. It's not really spanning tree's fault per se, but it's something where maybe the design we're bridging VLANs that we shouldn't be, and so BPDUs don't get recognized, or there's a legitimate issue on the switch where we should have been blocking a port and we didn't, and it ended up forwarding traffic. We had that a couple pretty bad issues a number of years ago that caused that. But yeah, those are going to be your top 3.
Okay, so typically a change, right? Someone did something, and of course, when you ask, no one did anything, and then you figure out the misconfigured server or third-party device, or
it is the amount of times I have asked what has changed, and they swear up and down, oh, nothing changed. And then eventually you get to back on the Nexus switches, we had a feature we like to call the liar logs, which was a way to see all of the configuration commands that have been configured or run on the switch. And sure enough, you say, all right, well, the logs showed that this happened at 10:37:02 p.m. And you'll find a configuration change that happened down to the millisecond. There is no question that this configuration change directly caused this issue. And the customer tells you, oh, well, that shouldn't have caused this problem. Oh, well, okay. If we're using that logic, then, and usually it's not through malice or anything bad. It's a lesson learned that sometimes when we look at how protocols and how devices are connected, the path is not always as linear as we might think.
I've had situations as well where, I showcase like this username caused this config that, brought the whole network down. And they're like, oh yeah, well, it wasn't me. And I'm like, well, it's your user ID. So, and they're like, yeah, but okay, I'm not the only one using it. I share these credentials in a WhatsApp group. So one of your colleagues did this. And of course, he's not going to, raise their hand. So
yeah.
You have a problem, sir.
That's usually how I ask him, am I on speakerphone? If the answer is yes, all right, take me off speaker. I'm like, are we done here? Do you want me to just send you a very generic summary email? And they usually go, okay, yeah, we know what the root cause is. Yeah, lessons learned for a lot of folks. Some of them the hard way.
What kind of, because you talked about SEV1s, and okay, there's always exceptions, but SEV1s are typically simple because it's a number of issues. You can take a drastic measure to fix it, and then once it's fixed, everyone happy. You can work on the root cause, but you have time. What kind of more complex, crazy issues did you face?
Yeah, no, you hit the nail on the head there, and it's one of the reasons I loved them so much. You could take the case; it was usually instant satisfaction. You run one configuration command, or you shut a port, it goes away. You seem like the hero. But there's one case that really sticks in my mind as one of the more difficult ones that I had to solve throughout my career, and it has to do with a utility company for the state of Texas, which for anyone not part of the US, Texas is one of our largest states in terms of just overall landmass. And this particular utility company, because it's a utility, they have a presence in pretty much every single major city, town, county, etc. Like they just have a massive presence all over the state. And what they were trying to do was they had a way to read the utility usage digitally for all their customers in these different cities at once. And one of the problems they were having was normally this digital reading would happen over the course of, say, a couple hours for some of their bigger cities. But right now it was taking 24 to 48 hours and was still failing. And so they come to us and they say, look, this is, even though it's slow or failing completely, this is a big deal because if I'm polling, say, 500,000 people, if I can't get their usage, I can't create billing. And so you can imagine just your own electric or other utility bills, what this translates in terms of lost revenue or potential lost revenue. So this was a pretty big deal for them. And they had tried to solve it on their own, couldn't. And so they brought in us. So this comes in as a Sev 1. I accept it on like a Monday, and we figure, okay, let's start with the basics. You've got application slowness. I have no idea how your application works. Let's start with some packet captures, see if we can kind of reverse engineer how this is supposed to function and go from there. Fortunately, this particular user, they had access to the local server that was collecting the hundreds of thousands of records and sending them across. And we look at the capture, and it's pretty easy to see that the issue is packet loss because we have a single TCP stream going from their server to a destination server on the opposite end of the state. And Wireshark is really nice in terms of its ability to highlight loss. If you're familiar with it, it's red on black. You really can't get any more obvious when looking at it. And it's 1% to 2%, which is pretty catastrophic for a TCP flow. You can get near line rate speeds, but if you've got 2% packet loss, you're lucky to get 1 or 2 megs, especially when we're dealing with a wide area network that has 50 to 60 milliseconds worth of latency end to end. So this is a big deal, to put it bluntly.
It just breaks your window, right? TCP window is like reduced a lot, and your throughput goes
exactly. Every time you get one packet lost or a group of packets lost, TCP is going to window down, and it's going to keep windowing down as long as there's loss. And the moment it tries to window up, because it doesn't window up at the same rate it windows down, it'll try to window up, and it gets more loss, and so it stays perpetually low the entire time. So knowing this, we say, all right, it's packet loss. When you see retransmissions, it is packet loss. You're going to hear me say that multiple times because at this point in my career, that's what this means. This is a definitive. Retransmissions are packet loss. And in order to troubleshoot this, you have a chain of switches, and it's pretty simple. You log into each one, and you look at all the counters to try to figure out where's the loss. But this is where things get a little complicated because, one, the customer had already checked this on their own, and they're now asking me for some additional help, a way to dive into it deeper. And this was also in the height of our Catalyst 6K days, which one of the largest selling products Cisco ever made. It's what essentially put us on the map. The Cat 6K, it was used anywhere and everywhere. It is a beast of a switch, super serviceable. There's a command for nearly everything. It's just, I love the box. But it's also bad because, also kind of harping back to our earlier conversation about being an engineer working all these Sev 1s, even the rare issues become common for you. And every engineer will tell you that as you start troubleshooting some of these weird one-off issues, you get this little, I'll call it maybe a resume of weird one-off commands that you now use every single case you pick up. And it's weird stuff, right? Like, oh, I worked some case where this individual bit that no customer will ever see in their lifetime, it was set to 1 instead of 0. It was like the X tag bit or something that is otherwise meaningless. And now as an engineer, every single day you check that bit because you're hoping for that one case every 6 months, you're just going to look like a hero. And so I have like 20 of these commands at this point. And I say that because given this is a utility company, I need to trace the path of this packet. And they have 6500s. I have this slew of commands that I could check. And because it is a metropolitan area network as well as a wide area network, the end-to-end hop count is like 30 switches because they have VSS, virtual switching system. We take 2 chassis, combined them to act as one big virtual switch. And because it's a utility, they also have redundancy everywhere. Everything is interconnected. There's lots of redundancy because there's always someone out there with a shovel or an excavator pulling up fiber lines and stuff is going down. So this is a robust network with lots of possible paths. And
But you're talking layer 3 hops, right?
it's a combination of layer 2 and layer 3 because the way they had this connected, imagine every city, imagine your country or your state, wherever you might live in here. Imagine every single city was interconnected. And within the city, the cities are multiple layer 3 hops, but then each one is maybe a formal data center or it's a colo. So there's switches there as well because they also have to connect a lot of their infrastructure. And so this is, I would say, at least 15 layer 3 hops, probably at least that many layer 2. And it's a big network. And the other problem is because we can go pretty deep on them, it takes a while to look at all these. I mentioned I picked this case up on like a Monday. When I do the initial check of all of these intermediary devices, we find no loss. And this took like 2 days to check every single one in depth, in detail, looking at every single possible command I could. And this is where we now come to an unfortunate conclusion is we might be facing silent packet loss, which is every engineer's worst nightmare because packet goes in, it does not come out, and the switch doesn't tell you that it doesn't come out. It doesn't even know that maybe it got the packet. This is a nightmare for TAC engineers. And so
This is the word. It's like silent crash, the box rebooting without any log. You're like, what can I do about this?
Absolutely. And so, and with silent crashes, it's like, okay, you end up, the amount of work required to troubleshoot this now increases tenfold because you have to try to be sneaky around the problem and prove which device is at fault.
And this is worse because you have 30 hops. So it's a lot of places to do a lot of work.
The Catalyst 6500 did not support a reliable embedded packet capture. A lot of our switches now, we have a way where we can run a packet capture on the device. But if you're looking for something like silent packet loss for a stream that is already lossy, you don't want to risk that. And then it turns out that the device dropped your packets as part of the capture and not were genuinely lost. And so as a result, this means we need to collect physical spans. Texas, as I said earlier,
is very big.
Is a tremendous state. And half of these hops are located in like colo data centers that are not easy to get to. And so I'm trying to level with this customer. And this whole time I'm showing him all the data I'm collecting and what we're chasing down. And he's in agreement that, it looks like silent loss. You did a very thorough look over the switches, and we have no choice but to collect packet captures because, again, TCP retransmissions equate to loss. His location at the time allowed it where normally we would go right in the middle of the network. So if there's 30 hops, you go at number 15, you get the capture there. If you see the missing traffic, at least the first 15 hops are good, and then you kind of focus on the other half, and it's a problem of just trying to cut this in half every time.
Yeah, bisection.
Exactly. But driving 8.5 hours to the middle point is not exactly the first thing that this customer wants to do, understandably. So we end up spending another 2 days with him calling colleagues. At one point, he was driving to some of these other centers, and we're trying to get these packet captures. And every time, it's pushing us further and further out. And so now here we are on a Friday, and we say, all right, we are now in the destination data center. And again, I can't impress just how much work has been done. These are 8 hours a day, all day. The only break we took was like for lunch. This poor customer has hundreds of miles that they've driven trying to get these packet captures between them and their colleagues. And we still can't find this packet loss, but we know it's there because retransmissions are everywhere. We get all the way to the destination data center. We find the server that's supposed to be receiving this traffic gets the packet that is otherwise lost, ignores it, and then the sending device, upon not getting any sort of acknowledgement, automatically sends a retransmission. And then the server, for whatever reason, goes, oh yeah, this retransmission is good. I'll process this one. And then goes on and continues now sending acknowledgments. And so here I am. I'm like, oh man, I just spent a week of my life troubleshooting what is essentially a non-Cisco issue. This has nothing to do with switches. I just proved your packet went all the way from the source to the destination, made it to the server. We did a TCP dump on the server itself, and your server's ignoring it. And customer looks at me and goes, Chris, I agree with you, but what I can't figure out is, we had a fiber cut a few weeks ago, and we found that if I adjust the routing to use these different hops, this problem goes away. And so we joked a little earlier about how, customers say, oh, nothing changes. It's like, oh, well, that shouldn't have caused this, but clearly it does. It is incontrovertible. If they change the routing for a device that is like 15 layer 3 hops away, it causes a server in this data center, and only this server, mind you, to all of a sudden start recognizing random TCP flows. And I like this story because this is one of the instances where I like to say that I got it wrong. Because I'm sure you guys remember when you were maybe a more junior engineer, and I know this for myself as well, you would get a case, some of your earlier cases, and you didn't know where to start. And you would try certain things, running commands, and nothing really made sense. And you would call over a team lead or a more senior engineer, and they just had the magic fingers. Every command they touched, everything they looked at just had exactly the answer that you completely ignored, and like that they could do no wrong. And this is one where I was kind of in that position of, yeah, every command was right, that everything was going right. But then I realized it was this peripetia. I got it completely wrong. There was something in the network that was causing this server to ignore it. And it broke all my training at that point as well, because if you know IP, there's nothing that a layer 3 device should ever do in the IP header that causes a device multiple hops away to ignore it.
That causes some trauma on my side because, like you already feel proud at some point. Like I went the extra mile and I helped the customer to prove, the issue is not on the Cisco side. And then you feel like, I should get some glory. I did extra steps and everything. But you have to be super certain that the issue is really not on a Cisco side. And a few times I've been like overly confident, I did this, and this. We just proved it's not a Cisco problem. And then because of a weird turn of events, it actually still is a Cisco problem, or at least some interrupt or something, right? So you have to be 1,000,000,000% certain before you drop the ball. And I feel this is where you're going. So I have trauma now for a lot of cases where I was overly confident, and it taught me to be humble over the years.
Absolutely. It is an ego hit, to put it bluntly, right? And so, all right. So looking at this, I've got proof that this now must be a Cisco problem. None of the data makes any sense. And so we end up having to just throw out all the current theories. I mentioned earlier, we have TCP packet loss. This is TCP retransmissions. They're caused by packet loss, but I have no loss. So what else could it be? Through sheer luck, through this multi-day journey of collecting physical packet captures, we got lucky in that some of the captures we collected were of the devices that were otherwise bypassed when we changed this routing information. And for anyone who's ever looked at Wireshark, a lot of people will automatically hide. There's 3 windows that appear by default. You have the packet view, like all the packets. It's a big list of packets with just high-level info. Then there's a more detailed view. So any one packet selected, you see all the headers and you can expand it out. And then there's another that is the raw hex of the packet. And a lot of people will put that away because, hey, who reads raw hex these days? Well, in this case, I still read raw hex on occasion. And I had the 2 packets exported, the original packet and the retransmission, and I'm just going back and forth with the up and down arrows on my keyboard trying to figure out what is different between these. L2 header was good, L3 header was good, L4
Wait
header
a second.
was good.
The retransmitted packet is accepted by the server at the end, right? So that's why you're comparing the
is.
2. Okay.
Yes,
So the original packet gets dropped, but then the retransmission works. So one of them has something wrong that makes the end server drop it, and then the other is valid somehow, right? Okay.
Exactly. It's the 2 packets, the one that should have been accepted and the one that was retransmitted. These should be identical packets carrying the identical data. And the only thing I can think of is the switch must be fooling with something in the L2, L3, or L4 header. The L2 header, well, that changes every L3 hop. The L3 header, the only thing that's really changing is the time to live value and a little bit of the IP header checksum because the time to live changes. And then we've got the UDP header, or I'm sorry, the TCP header that doesn't change as well. And so I'm going back and forth, and through sheer luck, I see deep in the packet, like 1,000 bytes in, I see a value going from 7F to FF, which for hex, a 7 in binary is 0, 1, 1, 1. And F is 1, 1, 1, 1. There is one
So 1 bit
bit.
difference.
Yeah, a bit flip.
It was a bit flip, which, and I can tell you, I've been at Cisco for 15 years. I can count on one hand the number of cases I've had involving bit flips. And in this instance, what we eventually determined was the switch was getting the packet. And this is maybe a little dive into the architecture of the Cat 6K. We would get the packet, do all the outer header checks and everything else. And then the module that receives this packet carves off all of the L2, L3, and L4 headers, carves them off separate from the actual payload of that packet. The payload is stored in a little block of memory, while the headers go to the forwarding engine for us to make all of the decisions. And that's everything from MAC address rewrite to decrementing the IPTTL, maybe recalculating something in TCP if we have to fragment or not, or ACL, all that good stuff. And then once we have that result, that goes back to the module. And the module now has instructions from the forwarding engine that says, okay, rewrite the IP header and rewrite the MAC address and now reappend that payload and send the packet on its way. And what was happening was a block of memory had failed. So in the microsecond that it took to store that payload while we're looking up all that header information, the bits were flipping in random parts of the payload. And so now when the switch put it all together, it calculated a proper checksum for the packet, but we reassembled the packet, sent it on its way, and it wasn't until we got to the destination server that was the first device with enough intelligence to realize the payload is bad. And the application wasn't intelligent enough to articulate that in any way. It simply just ignored the packet and perpetuated this problem. And that's one of my more interesting stories, where it took a week and multiple packet captures and one poor customer driving halfway across the state of Texas in order for us to figure out we had a single block of memory that was bad and flipping random bits.
Shouldn't ECC memory detect that and crash the box?
Okay, so in ECC memory, yes, but not all memory is ECC, because ECC memory is a little bit slower. And so when we think about packet forwarding, and also for cost reasons, which, I'm not a product manager here, so don't shoot the messenger, but not all the memory on the Cat6K was ECC. And so this was something that normally we could do like a scratch test or a write test where on boot up, we could fill up these memory blocks and read them back and see if anything comes back that is incorrect. But in this instance, we couldn't check that. And usually it's going to be like your system memory that's used by like the operating system, where we're going to make that ECC. But all the actual memory that exists on the chips, on the dies, it's not always error correct.
Can you go over again the point of why the last server was able to figure out the problem and drop, and not the switches on the way? Because I'm not 100% clear on that.
Yeah, so we'll break this down a little bit. So from a switches perspective, when you first get your packet, you've got standard checksums on the end. Everyone hopefully knows about the frame check sequence that happens at the end of your layer 2 header. You also have this for the IP header, and sometimes depending on L4 header, if it's there, you might have a checksum as well. When the packet comes in, one of the first things that happens, and this is common across pretty much all switches, they will have a dedicated ASIC or chip that does nothing but CRC calculation. Because if the CRC is bad, it doesn't even make sense to continue processing the packet. So we check the CRC, and it is a valid packet when received from the peer. And knowing that it's valid, we then need to split off all the internal headers, but we also need to add some of our own information, like what physical port did it come on, what VLAN, anything related to packet forwarding. And that would all go towards what we called our EARL, the Enhanced Address Resolution Logic, also known as our forwarding engine. And the EARL doesn't care about the payload of the packet. It only cares about the headers. And so the payload just gets stored off to the side, as I mentioned earlier. Now, when we think about the forwarding decision, the EARL also needs to take into account things like your TTL. Sometimes we might fragment a packet. Well, if you fragment a packet, you're changing the size and maybe removing some of the payload, which means we also need to have the ability to change the layer 3 and maybe even the layer 4 checksums for that packet if it's being fragmented. So all of that header information has the ability to be modified by the switch. So your payload, again, painting the picture here, your payload is being stored in memory. All your headers have their checksums, and they were all valid. Then when you make your forwarding decision, we know, even in normal circumstances, many of these headers may need to be recalculated because at a minimum, your IP header, you're going to be decrementing the TTL. Well, if you change a value in the IP header, that means your old checksum is no longer valid. You need a new checksum to include the new lower TTL. And then same with the frame check sequence of that packet, because now that's going to include the layer 2 info, layer 3, layer 4, etc. So all of these checksums are built brand new based on the decision of the packet. And I mentioned TTL, but it could be maybe we're changing the QoS value as well. There are certain features, like if we're doing something like NAT changes the L4 port numbers. If you're changing L4 header information, you may need to change checksum info there as well. So the switch just will look at everything and say, okay, well, based on the existing data, which is not kept, we don't have any checksums specific for the payload. It's something we reassemble onto the packet. And now with all the new layer 2, layer 3, and L4 headers, we now need brand new checksums. Well, because the payload, we have no idea, it just got corrupted. So we put what is essentially a bad payload back on the packet, and then we calculate a checksum. Well, the checksum, because it's being done right then and there, it is valid. It's valid for invalid data. And one of the last things we do before the packet goes out on the wire, the same ASIC that checks the CRC is the same one that imposes a new CRC on this fully reassembled packet. And so from hop to hop, everything is correct. The switches have no idea because, again, they're only checking IP headers. We have no idea what the payload is. And it's not until that server gets it, because now the network did its job. The IP headers and everything was always valid. The server gets it, and now it's expecting some sort of, I assume, application specific formatting, and that bit flip results in something that is off. And the application itself now is realizing that this data needs to be ignored, and it had no mechanism at the lower levels to tell it was bad. It simply just ignored the bad data, and TCP as a result would automatically retransmit it because there was no acknowledgement. So hopefully that helps explain. But it was, like I said, this is incredibly rare, because when we think about switches on the whole, right? Cisco has, we assume, millions of switches out there. We've been a company selling switches for 30 plus years, 40 years now at this point. So you think about how many devices out there, how many ports we have, billions of ports moving thousands of packets per second each. And despite that scale, this is something that, again, I can count on one hand the amount of times that it's been seen. So it's exceptionally rare, but that's also what you run into sometimes with
If we would have had an occurrence of this hitting like the header or something, we would have seen a crash, or we would have seen a memory corruption, and we would have spot that super easily. But just because of the coincidence that this was happening only inside the payload, the thing that the switch is not supposed to look at, made it the whole adventure that you just mentioned.
So that's, that for anyone out there, if you ever think about the joys of TAC, that's just some of the issues that you might experience. I would say, again, lots of catchy headlines out there between, in this one, it was the big utility. The headline maybe wasn't as impressive, but then others like, the president's about to learn your name, or we're going to bust down the doors of this hospital. They're usually a bit more exciting, but yeah, it's a fun and interesting perspective sometimes, because you get to see a lot of how this stuff is used, and a lot of it is very surprising, because you just don't realize how interconnected the world is these days, and how much it relies on this stuff.
Yeah, so for me, switching has always been this thing that hasn't changed in 30 years. Like the set of protocols, the set of technologies that are involved. The only thing that evolved is basically the speed. And I'm sure I'm wrong, and I'm sure that I'm missing something. So can you tell me what's new in switching?
Oh boy. All right, so that's not a loaded question, right? What is new in switching? Well, I will say I had a little bit of the same mindset and a little bit of apprehension when I first thought about switching when I was a junior engineer. Like, yeah, it's spanning tree and MAC addresses. How interesting could this possibly be?
Yeah.
But the reality of it is our switching team within TAC is more of like a platform and kind of generalist approach in terms of, the protocols. Spanning tree's been around for 30, 40 years. But the ASIC architecture of all these switches changes every couple of years. And the amount of, I would say, application and protocols and like layer 7 and 8 type stuff that's running over the network is ever changing. And so when we look at, what does an engineer do? Engineers are not helping customers with like basic spanning tree configuration. Instead, it might be something that's more architecture or performance based, where, okay, we have a network need where I need to move a lot of traffic, and I have, say, using like older stuff here, say 10 gig interfaces. This switch might have 48 10 gig interfaces on the front. Well, can all of those interfaces run at line rate? What happens if you have network monitoring software that wants a copy of every single packet on the network so it could use it for intrusion detection? Or what happens if you want a mix of the full internet routing table, which right now is at like 600,000 or 700,000 routes, plus you have a multi-thousand line ACL, plus you have policy-based routing, plus you want to redistribute some of those routes from BGP into OSPF or vice versa, and now you have this whole mix of features. That's where we start getting into architecture, and ASICs, which that's also something that just fascinates me, because if we think about, and I'll talk a little bit more modern now, talk about our Cat9K switches with Silicon One. These ASICs, as they stand today, when we talk about packets, it's lookups per second, right? Again, we're looking at that L2, L3, L4 header. The ASICs we have today can have a routing table of over 1 million routes, some cases over 2 million. We could have, I think it's like a 16,000 line ACL, multiple comprehensive QoS policies on the order of thousands of potential operations, IPv4, IPv6, security, everything you can imagine. Our configuration guide right now is sitting at about 18,000 pages. So imagine all that stuff, and we can look up packets. We could check them against a 2 million route table up to 1 billion times per second on the low end. Some of the stuff we have coming up now is multi-billion packet lookups. And so how do you fit all of these features into a chip and you can still maintain some of that speed? Or what happens if, when you configure that span session and you say, hey, I want everything duplicated now? Well, what does that have in terms of hardware performance? Or if we get into latency, one side note, stock traders, they are a group of folks that they don't care too much about the protocols or the brand or anything else. They care about pure hardware performance. If you could save me a microsecond, I will buy your switch over a competitor's because they're using it for all this high frequency trading. That's all the architecture. That's a lot of what switching does. Is engineers have that ASIC architecture. A lot of them have it memorized in their head, but then also the software side to say, all right, if I have a switch that has 600 ports, and each of those ports is running spanning tree, and each port has 100 VLANs allowed, and if I'm running rapid per VLAN spanning tree protocol, that means one BPDU needs to be sent for every VLAN on every port. That's a lot of BPDUs. And then what happens from a redundancy perspective? If I have 600 ports and 2 supervisors, which, mind you, they are the brains of the whole operation, if I now change supervisors, or a new route comes in, or a spanning tree topology change happens, and I need to clear out 10,000 MAC addresses, reconfigure all these VLANs, do all this stuff, and I need to do it in less than 2 seconds, or really 6 seconds, because that's our default timer for when BPDUs time out. How do we handle that? And what's the limit? We have ASICs that can move 2 billion packets per second, but then I have a CPU that's lucky to handle 23,000. So there's a huge discrepancy, and that's a lot of what our switching team is focused on, is how does this hardware perform? How can we tune it so it's running like an F1 type race car? We want this thing running as fast as possible, keep the utilization of some of these finite resources down to a minimum, and then following that, so that when we start coming up with these really complex solutions, everything from fabrics and VXLAN and everything else, but also just application level stuff where it's, hey, we're hosting a virtual meeting and we just need overall low latency or this many flows or whatever it is. That's where we get into the switching team. It's not spanning tree and BPDUs and MAC addresses. It's ASICs and software architecture and performance and everything that comes with it. So hopefully maybe that teases you a bit to maybe consider switching into the future, right? We're a lot more than just switches and L2 loops these days.
Yeah, it's basically the whole network, right? A lot of variety there.
It's the whole network. And I think we had mentioned earlier, if the wired network goes down, so much is built on top of that. That means the wireless goes down. These days, we all think, oh, wireless is king because everything has a wireless connection. But behind every AP is still a physical switch. And when they go down, oh boy, everyone panics. So
yeah. People blame the Wi-Fi, but then it's the switch being.
Yeah.
I know. But
and I think that's a beautiful conclusion, actually.
Okay, Chris, thanks a lot. That was a super interesting episode.
Yeah.
It was great to have you on.
Yeah, no, I appreciate you guys having me, and hopefully I painted a relatively rosy picture of TAC and switching here. And yeah, super excited to be on, share the stories, and happy to do it again sometimes if we ever get anyone who wants to know more about switches or hear some more stories where the president did not learn my name.
That would be the title of the episode.
Thanks for listening to this episode of the Cisco Tech Stories podcast. You can subscribe to us on the Cisco Podcast Network in SoundCloud or your favorite podcasting app. You can also find us on our own channel called Cisco Tech Stories in every podcasting application. We are also on X at Cisco Tech Story without the S, and on Instagram and YouTube at Cisco Tech Stories. Thanks, and see you next month.
They called me Chris with a K, not a C. But that day it didn't matter much to me. The sky was split with a restless sound. The nation shook while I stood my ground. And I swore to the sun, to the wind, to the flame that history would never know my name. The day Obama did not learn my name, no headlines scream, no medals claim, a quiet hero in a loud refrain. The day Obama did not learn my name. A code red blinking like a warning star, a crisis waiting just to go too far. But I cut the wire on fate's design. The clock struck zero and the world stayed fine. And I whispered to shadow